Hi, welcome to Trig.
We're calling this Trig because we're learning about triangles.
Kind of. It's actually, we're going to be learning about circles, as you'll see soon. If I were naming this class, I wouldn't call it trigonometry, I would call it circles.
Ponder on that for a while.
So there are three facts that we're going to use implicitly and explicitly throughout the whole, throughout all of this year. And so today we're just going to spend time fleshing out those facts. One, and this is one we're not going to prove, you should know this, or have seen this before, is that the sum of the interior angles of a triangle is what?
180.
180 degrees, 180 degrees. Okay, so this is something you already know. We're going to use that implicitly all the time, implicitly and explicitly all the time. We're not going to prove this one. Have you seen a proof for this, either of you?
No.
I was wondering if maybe you did it in geometry, but maybe not. Either way,
Wait,
it
I
doesn't.
think I did.
Right? It sounds like something that you've done in geometry. But at any rate, this is the one thing that's absolutely fundamental, but we're actually not going to prove it. It would take too long, and the other ones are way more important. But we're going to use this today. So, in fact, let's just start. Let's apply this. And one thing I'm going to do in this class, what does that mean?
90. Right angle.
It's a right angle, which means it's how many degrees?
90.
90. So if I say, so now we have two other angles. And let's say, for instance, that this angle happens to be 30 degrees. That means that this angle must be what?
60. Yeah.
60, right? Okay. So anytime you have another way of saying what I just did is anytime you have a right triangle, one angle entirely determines the other angle, right?
Yeah.
Like if I'd said 15, you would have said, I don't know, 75, is that right?
Yeah.
90 minus 15.
Yeah, right? Whatever that is, it's entirely determined. So a right triangle is entirely determined by one angle, given that one of the other angles is already decided, that is the 90-degree angle. Okay? Now, here, this is where it's going to be fun. All right. So starting with any right triangle, so of course in this class, and this is just everywhere, a right triangle is one whose one of their sides is 90 degrees. Given any right triangle, let's say that its length here is A, let's say its length there is B, and its length there is C, what can we say about those lengths? How can we relate them together?
A squared plus B squared.
There you go, right? And what do we call this? This is the what theorem?
The Pythagorean.
Pythagorean theorem, right? Have you seen a proof of this?
There is one.
Yes, there is.
There is?
And we're going to do it.
It's called the theorem. So it's theory, right?
No, theorem, it just means statement with proof.
Oh.
That's what a theorem is. Theory is different. That's a whole bunch of stuff put together in some kind of framework. Theorem is just a statement with proof. And so we're going to prove this right now. Now, okay, it's going to be one of the few times, there will be maybe two other times this year where I'm giving you scissors. Do not hurt each other with these. I swear, if you guys start fighting. And now here are four, this is four, and this is four pieces of cardstock.
What do we do?
I'm all quiet, like, wait, what's going on? Make sure, find an edge, like stack those like this, so they are absolutely 100% like a very nice, make a very nice right angle right here. Maybe you can see where this is going. What I would like for you to do is this. So here's your cardstock. And here's your nice flush right angle. What I'd like for you to do, and wait until I'm done talking about this before you do this, take your scissors and cut off a corner like that. Now, You could do this a bunch of different ways. I'm going to ask that you don't do it so that you have equal lengths, right? And I'll just say, like, if you did do it that way, everything we're about to do is perfect. Like, everything is going to work just fine. But just so that what I'm going to draw on the board is going to be similar to what you guys are going to be doing. Another thing, don't make it too big, because you're going to be fitting these onto your paper and tracing over the whole thing. So and also don't make it too small. Come on, use your brain. So try to make it to where one side is obviously bigger than the other. Of course, it doesn't need to be exaggerated like this, but just so you know that there is a smaller side, a larger side, and a hypotenuse. Go ahead and do that. You want 4 equal-sized triangles. All right. And if you lose those scissors, my wife will kill me. So please don't lose those scissors. Okay, cool. And you're going to want to get like a fresh sheet of paper for what we're about to do. Okay, here, actually, let me get this stuff back. Get this out of your way. Thank you. Okay. Now, this is what I want you to do. So first off, watch what I'm doing, but don't actually do what I'm doing. So we're going to arrange this in a certain way, your 4 triangles. Since I only have 1 triangle, I'm going to put this down and trace over it. I don't want you to put it down and trace over it. But what I want you to do is arrange them on your paper in the following way. Let's start with the small edge on the bottom. And if you did it the other way, it wouldn't matter. Everything would work out just fine. But just so we're all on the same page and we're all making the same, generally same looking thing, start with your first one right here. Put your first triangle down. You're not tracing over it, but I'm pretending now that I've just placed my first triangle like that. Just like that on your page. Now take the second one and do small side here, long side like this. And you want to make it as close to straight up and down right here as possible. So that this is one straight line right there. Like that. Okay. Oh, and one thing I meant to say before I started all of this. Let's just all agree here that the shortest side of your triangles is A, that length, we're going to call it A. The longer side, the bottom as I'm holding it here, is we're going to call that length B, whatever it happens to be. And then the hypotenuse here is what we're going to call the length C. Okay, so now we've just done this one. Arrange another one like this, so that the top, just like this, and again, straight line. So as you can see, we're kind of constructing a box here of 4 triangles. Oops. Like that. Okay. And then the last one, we're just going to rotate and put right here. And if I were perfect, which I'm not sure if you guys know this or not, but I'm actually not perfect. I know that may come as a surprise. But if I were perfect, this would fit all nice together. Oops. Oh man. Start making jokes about perfection. I just like really mess this thing up. Okay, so just like that. So that's how you're arranging your 4 triangles. Now I actually do want you to draw on your sheet. I don't expect you to do that, and this does not need to be perfect, but what we're going to do is just trace a box around all 4 of your triangles like this. And I'm going to do it dotted so we could tell, well, I guess I don't need to, because I have different colors here. Just trace a box around. It doesn't need to be perfect, but we're going to pretend that it's perfect. We're going to pretend that this pink box that I drew and the box that you actually drew on your page is exactly the same area and exactly touches where these triangles touch. And there's two more things I want to do before we actually start talking about what we're doing here. Right now we're just doing the setup. So when you're done with that, I'm looking at the camera, by the way. I just want to see how well this is coming out. Okay. And if you know, like, if they're not staying exactly perfect, that's okay. But, like, okay, so that's good. All right. Okay, that's good. It doesn't need to be that good. So this is the idea, right? Like, we're pretending that that box, which is not drawn perfectly, is exactly the same, right? But we're just doing it. Now, this is what I want you to do next. For where every one of these triangles meet, just put a little tick mark right there, 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 and there. Now we're going to label the lengths. And I said that the smallest of them we're going to call A. So that means that this out here, and so on your page, I would like for you to write on the outside, A, right here. And I'm going to go around clockwise here, yes, clockwise. Then this longer length should be B. This length right here should be A, and B, and A, and B, and A. There we go. All right. Oops, and B. Okay, so everybody good? Everybody have this? Okay, so now I'm going to ask you a question. From here to here, what angle is this? How many degrees is that?
90.
How do you know?
Because it's
Oh, it's a square.
Well, it looks
looks
like a square, but looks can be deceiving. How could we know that it's a square?
All the sides. Well,
Well, let's think about what we just
all the
did
sides are the
before.
same length.
yeah, they're all A plus B, right?
They all, okay, so
Well,
that's one way.
wait.
You could say that all of these sides are the same length, and so when you slap them all together, how could it be anything other than a square? Another way to do it is this. You could say, well, the smaller angle here, whatever it happens to be, let's just call it alpha. And we're going to be using Greek letters almost all the time to denote angles. So alpha, beta, gamma, right? And we're also, more often than not, we're going to be using theta and phi. But just so you know. And so if that's the case, let's think about the first fact that we talked about. If that's angle alpha and that's angle beta, what did they add up to?
90.
90, because that's 90, by construction, like literally this is how we constructed it. We had a right angle and we cut something off, so we know that's 90. And so that plus that must be 90. And so here's alpha, here's beta, and that's a straight line, ain't it?
Yeah.
Well, I mean, in perfect world, we would be able to line this up exactly straight. And so, if that's a total of 180 degrees from there to there, then what's left over? 90,
yeah.
right? So, whatever that is, plus 90, plus whatever that is 90 plus 90. So that has to be 90. Ditto that one, and that one. So, indeed, we do have a square. And what's the area of that square?
Oh,
C
times 4. No, C squared.
C squared, right? Because we didn't label the C's. We have the A, B. Each one of these lengths is C. If that's C and that's C, you multiply C times C to find that the area is C squared. Now, I want to write that down. So, inside the box, right? Inside this box, whatever, and I don't care about the area, the total area of the box. It turns out it would be A plus B squared, but that's not my concern right now. We have the pink box. Inside the pink box, we have a certain uncovered area, right? You've covered up this with one of your triangles. You've covered up this. You've covered up this. You've covered up that. The uncovered area. In fact, this is so important, I'm going to write it down. The uncovered area is equal to c squared. Does everybody agree with that?
Yeah.
Is there any way that can't be true? It has to be the case, right? Okay, now before we move on, let's just say for us that I had some box and I had some shape. I don't know. Maybe it's just a rectangle like this, and I put it in there. I put the rectangle in the box, and I said that the uncovered area in that box, uncovered area is equal to, say, 3 square units. Now let's say that I took that box and I moved it. Like I didn't, and no, I'm not stretching the box, I'm not compressing the box, I'm just taking the box and I'm just going to move it down here. What's the uncovered area of the box?
3.
I haven't changed it, right? For every 1 square whatever I cover up, I've uncovered that because this thing is not stretching, it's not compressing. I'm not bringing it outside the box, right? There's no tricky stuff going on here. All I'm doing is I've just moved it inside the box. Okay. So, the same should be true for your 4 triangles. If you can move them around, and as long as they're not overlapping, or you've pulled them out, or you've stretched one somehow. I don't know how you stretch cardstock, but if you found out a way to stretch cardstock, we're not doing any of that. As long as I just move these triangles, then the uncovered area should be exactly the same, right?
Yeah.
Like if I took this one and moved it this way, yeah, this part would be covered up, but all the part that I've just opened up, it would still be, the uncovered area would still be c squared. Okay? Okay, so this is what I want you to do. Take your top square and slide it down to here. Okay? And so I'm going to draw what that's going to look like. You guys will be way ahead of me, but I'm going to go ahead and do that. Let me get rid of this c squared. Bringing this guy down to here ends up looking like this. And then this guy is gone. Okay? Now what I want you to do is this. Take this one that's down here and slide it up so that it just touches right there. And so now that one looks like this, and there you go. And so now you've slid the top one up like that. Finally, take this one that was right here and slide him over so that he just touches right there, and everybody joins together. Just like that. Okay, is the uncovered area exactly the same?
Yes.
We have not stretched these triangles. We're not overlapping. As you can tell, I kind of did overlap as I was drawing this, but in the perfect world, we know that's not going to happen because
a squared plus b squared.
Right? And just to check a couple things, because this is the thing about proofs by picture is it's real easy for something to look a certain way. And if we wanted to spend a full 30 minutes just doing this, we could make a fully rigorous argument about, well, the length of this was A, and the length of the top part is A, and so they match up exactly like that. The length of this one is B, the length of that one is B, and so they match up. But it's pretty obvious to see what we're getting at here, right? So now, the uncovered area, what is this uncovered area right here?
B squared.
It's what squared? Remember, this is a little tricky.
A squared.
And there's a couple ways of thinking about this, right? Because we know that guy's A, that short length is A. This short length is also A, and we have the nice label out there, just in case we weren't sure, right? So this is what?
A squared.
Using the same reasoning, we could see, okay, there's that length right there. We've already labeled it, it's B. We've got that length right there. We've already labeled it, it's B. And so that area is what again?
B squared.
And so the uncovered area is equal to what?
A squared plus B squared.
Yeah.
A squared
Yeah.
plus B squared is equal to the uncovered area, which is equal still to C squared. And we've just proved the Pythagorean theorem. If we wanted to be fully rigorous, we could with this exact picture, right? But we would have to, make a bunch of things about right angles and complementary angles and stuff like that. I think it's pretty easy to see, like, yeah, this works. Cool, huh?
Yeah.
I think that's kind of cool. So, okay, all right. So we've proven the Pythagorean theorem. Uncovered. Yeah. Okay, we did all that. And so we will use this all the time in this class, and in ways that you might think, well, yeah, we're working with triangles. I imagine you're going to give me two sides and then ask me what the other one is. Yeah, we're going to do that, but there's even more fundamental stuff to where this is almost, you could think about this as like the central theorem of this class. Everything in this class that we're going to talk about hangs on this right here. And so I wanted to prove it 100%. So that we're all 100% sure that this is true. Do you believe that this is true?
Yes.
Awesome. Okay, great. So, and if you've never seen a proof before, it's pretty cool, right? I think the first time I saw it was on Wikipedia. Because I don't know if I did it in high school, but I remember trying. I was like, wait a minute, did I ever prove the Pythagorean theorem? And so I was like doing this thing. I said, okay, all right, we have a right triangle. And this is A, and so A squared would be this. If this is B, then B squared would be this. And if this is C, then C squared would be this right here. And then I spent way too long trying to figure that out. And then I got on Wikipedia and saw they have a little animation of what I just did. I was like, oh, it's brilliant. That's so cool. And so I wanted to do it. Okay, so, all right. So there's one other fact I want to talk about today. And the way I state this is going to be a little weird. And in fact, once I state this, we're not going to, we will only use this implicitly. We're never going to say, oh, because of this, we could do this. But it's kind of behind everything that we do in this class as well. So I want to spend some time working on it. So, the way that I write it is this. This is the third thing. You can scale the sides. Oh, wait. Yes. Oh, no, okay. Well, I'm sorry. There's another exercise I wanted to do, but I guess we'll get to it. You can scale the sides of a right triangle. And indeed, it's true for what I'm about to write. It's true for any triangle. But we're not going to need, if we wanted to prove it for any triangle, it would require another extra 30 minutes, and I don't want to. And as we'll see, the case for the right triangle is going to be more fundamental to everything we do in this class. And then from that, if we wanted to, we could build on that. But right triangles is really the bread and butter of this class. So, anyway, you could scale the sides of a right triangle by a constant multiplicative factor and the angles stay the same. What? Wait, what? Right? We'll get into that. And this is probably the most succinct way I could put this. But once I show you what I'm talking about, it'll make a lot more sense. So let's start off like this. Let's say that I have a right triangle, right there. And let's say that I give you two sides. Let's say that I say, this side is length 1, this side is length 2. Then what's that length? You might want to use your pencil.
One. Wait.
You
Oh, 2.
Right
Wait,
now.
no.
Like I said, you might
It'd be
want to write this one.
1, no,
Nope.
2 squared minus 1 squared or something. So 1 squared minus 2 squared.
Just work it out. It's so much easier. Just work it out. You would have been done by now. What'd you get? Or have you?
2.
Okay.
We're trying to find b, right?
Yeah,
So
you're trying to find b.
it'd
Oh,
be
no, the square root
b
of
squared
3.
equals a squared minus c
The square root of 3.
The square root of 3. And so what? And the way we find this, right, is Pythagorean theorem. We say whatever that one squared is plus whatever that one squared is equal to that one squared. And so we have 1 plus b squared is equal to 4. So we have b squared is equal to 4 minus 1, which is 3. We take the square root of both sides, and you're going to remember from last year, whenever
Plus
we
or
do that, we get a plus or minus. But in this case, we're going to throw away the minus because we understand in this case we're talking about an abstract triangle. There's no, it's not on a coordinate axis of any sort. If it were on a coordinate axis, like this, then we'd say, then the x value would be positive square root of 3. But if the coordinate axes happen to be over this way, then you'd say, that guy lives at negative root 3, right? So I don't want you to think, anytime you're talking about lengths, there's no negative numbers. Well, it depends. If you're on axes, then there absolutely are negative numbers, and this point right here would be negative root 3 on the x-axis. But we're not on coordinate axes. We're just floating off in, I guess, like the realm of Platonic forms. Like we have a triangle, and it's, in that case, yes, we're taking the positive square root of 3. And so I'm going to replace that right there, root 3. Okay, so what do I mean? So first off, this has it has 3. This is trig, so it has 3 angles, but there's 2 that we don't know. That one's obviously 90. This one, again, I'm going to call alpha and beta, just for right now. What I'm saying is that you could take a constant multiplier. So let's just say 2. Let's say the number 2. And if I multiply each one of these sides by 2, my claim is that what you end up with is a new right triangle. And its lengths here are, instead of 1, I multiplied it by 2. Instead of 2, what does it become? 2 times 2
4.
is, there you go. And what is 2 times the square root of 3?
3. Wait, not 2 or 3.
2, right? And my claim is, I have 2 claims here. Because naively, like you say, everything's going to fit together. Well, does it? I mean, there's this weird relationship here between these things and these things. In fact, the relationship has a bunch of squareds in it. And if you remember anything from last year, when you start putting squareds into an equation, things aren't nice and linear. Like, you don't necessarily move 2 units this way, you move 2 units this way. So there's no reason in my head that we should assume that just because you scale this by 2 and you scale that by 2, it automatically scales that guy by 2. So that's one thing we're going to have to check, is that this thing remains a right triangle. And that the angles, I say, stay the same. Now, so my claim is that when you take that triangle and stretch it out by a factor of 2, then this stays alpha, whatever it is, this stays beta, whatever that is, and that stays a right angle, or a 90 degrees. And so, how do I want to do this? Yeah, is this legit? So first thing I want to check is this indeed a right triangle? And to do that, I say, let's just use the Pythagorean theorem. And let's see, if I do that squared plus that squared, do I end up with that squared? So actually, I'm going to try to keep this consistent here and do it the way that I have been doing it. A first, A in this case is 2, plus b squared is 2 root 3. So what's 2 squared?
4.
And what's 2 root 3 squared?
4 times 3.
Good. And 4 times 3 is
12.
12. And 4 plus 12 is
16.
16 equal to the hypotenuse squared?
Yeah.
Yes, 4 squared is 16 last time I checked. And so it satisfies at least that. So we know that it's a right triangle. Okay, so that's nice. It does fit together, right? No, something funky doesn't happen with the hypotenuse or one of the sides. So at least we got that. But here's the thing that we don't know as of right now is, have the angles changed at all? And that's what we're going to prove, that they don't, actually. So how did I want to do this? Yeah, okay. First off, let's do so this was some particular right triangle. Let's do this in general. And instead of having actual numbers, let's just go back to calling them A, B, and C. And so we have some A, we have some B, some C. And of course, it satisfies, since it is a right triangle, we've already proved that it satisfies this relation right here. We know that that's true because it's a right triangle. Already proved it. So, now one thing, possible red herring that might have come up. I said a constant multiplicative factor. That I used one that was bigger than 1 so that we stretched the triangle out. The same is going to be true if we use, like, say, 1 over 2 or some really, really small number and shrink the triangle down. Everything that we're going to talk about is going to work for that. So the only thing is that I'm going to require that that whatever number we use, last time it was 2, I'm going to require that it's positive. We could, if we had a coordinate system, require that it's just non-zero. And that way we could talk about negative lengths, right? And so if this were on a coordinate axis like this, we have a positive length and a positive length, and then you could make them negative by flipping that down and flipping that over. That's not what we're talking about. We don't have a coordinate system. So the multiplicative factor, the constant multiplicative factor that we're going to multiply each one of these sides by, we're going to say it just has to be bigger than 0. Because if it's equal to 0, do you have a triangle anymore?
No.
You have a point, I guess. You have some point out in somewhere. So that's certainly not going to apply. Well, it still will apply, actually, because 0 squared plus 0 squared is equal to 0 squared. So, but you can see that's we're not doing that. So, okay. So I'm going to take whatever positive number I have, and I'm going to multiply every single side by it. So I have A times Z, B times Z, and then finally C times Z, like that. And now let's just check. Is this still true? If I take this squared plus that squared, do I end up with that squared? So, where am I? I'm there. Okay, so let's do it. AZ squared plus BZ squared. What's AZ squared?
A squared, Z squared.
There you go, that's how I want to write it. A squared Z squared plus B squared Z squared. Okay.
That.
Can we factor anything out?
Z squared.
I can factor out Z squared, and I end up with, I end up with what's left over in here?
A squared plus B squared.
And what's that equal to?
Z squared.
So C squared is Z squared. Is that the same thing as CZ quantity squared?
Yeah.
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 So it's still a right triangle. That's nice. At least, so, the whole reason I went down this route at all is because if the angles stay the same, well, at least the 90-degree angle has to stay the same. And if this changed at all by doing this weird stretching or compressing thing, well, if it's no longer a right triangle, it wouldn't satisfy that. So that's nice. In fact, it's not strictly necessary that we needed to take this step. But sometimes you want to take an obvious step to just check, because if the obvious step breaks and it's no longer true, well then don't waste your time doing the harder stuff, which is what we're about to do right now. So, slightly harder. It's still not bad. So, okay, at least it remains a right triangle. And you can see that also going in reverse, right? We could start with one that has already been scaled and say, well, okay, if something has already been scaled and we know it's a right triangle, then you end up with this kind of thing, az squared plus bz squared equals cz squared, and we just start moving like this. Divide everybody by z squared. Can we do that? Would we be dividing by 0?
Yeah. No.
No, because we're not ever scaling this thing by 0, because then everything's going to fall apart anyway. So of course we could divide everybody through by z squared, z squared, z squared, and we end up with this.
Yeah.
And so it works in both directions. If it had already been scaled and you scale it back, although, I mean, anyway, I'm just really wanting to beat that point home. It remains a right triangle. Okay, so here's the thing. So this is what we want to do. We're still going to assume z is bigger than 0. Look here. Z is bigger than 0. So now we need to check these angles. And what I'm going to do that. Okay, hold up. The end of the right triangle. Right. Okay. So here's this. I'm going to take. Oh, hi. He ate at 9, and only 6 ounces at 9. So he could be. And I have a 6 and an 8 in there. So, all right. You are welcome. So, what I'm going to do is I'm going to take this thing, and I'm going to slap it onto coordinate axes. You're going to see a lot of this. So I'm going to take this same triangle and put him right here. And right now, I'm not going to care what beta is. In fact, I'm going to forget that beta even exists. Why? Well, because, like we talked about before, if you have a right triangle, if you know one of the angles, you automatically know the other one.
So if alpha stays the same, beta has to stay.
Exactly. So if alpha is the same, and this doesn't matter, and this whole scaling thing doesn't, we never talked about that when we were talking from our first fact. The interior angles always sum to 180. If that one's 90 and that one's alpha, well, that one's completely determined. You don't have any room for play. If you know that's 30, that has to be 60. There's no messing around there. So I'm only going to focus on this one angle right now. Okay. Now, this one, the one that we started with, had some height A and had some width B, like that. And now let's think about this. This right here defines a line. And if I were to take this line and stretch it out, and just imagine this line going on forever and ever, and yeah, I guess we can go back that way too, whatever. This line has an equation. What is the equation of a line?
Y equals mx b.
There we go. And now we just need to find m and b. Oh, oops. I don't want to confuse that b with our other b, so I'm going to call this big capital B, so that we don't confuse because we already have another b being in. Okay, so what does b have to be?
0.
It has to be, right? Because when you plug in a 0 for x, here's my x, plug in a 0, we get out a 0, b has to be 0, or you could just say, well, the y-intercept is 0, so we know that that's 0. So what's m? Can we find it?
C. Right. No.
So now, forget about this. M is slope, which is what?
Rise over run, so A over B.
Rise over run, which is A over B, right? And just to really drive the point home, I'm going to actually forget this guy, and I'm going to put him right here and say the output needs to be A whenever the input, whenever we're here on the x-axis, here at B. Okay. And so, like you just said, it's what over what again?
Rise over run. A over B. Right, A over B.
Right. Okay, so M is A over B. Y equals A over B like just double check that we did the right thing. Plug in a b for x, and what pops out?
A.
Right, I'm going to really drive this point home, right? If instead of writing an x, I plug in a b, I plug in b for x, the b's cancel, I get an a, and that indeed is the proper output that I want. Okay, so let me rewrite this up here. This line is y equals a over b times x. All right, let's do it here. Now, let's take our constant multiplicative factor z. And without loss of generality, I could draw this two different ways. I could draw it as being bigger than 1, in which case it stretches this thing out and makes it bigger. I could draw it so that it's smaller than 1, and everything, so that this compresses and it comes down to here, and everything I say is still going to be true. So this is what I mean by without loss of generality, we could assume that z is bigger than 1. And so then when I multiply this side by z, I'm no longer at b on the x-axis. Instead, I'm at b times z, right there. Now what happens when I plug him into there? What do I get? It's my output. So let's see. Y equals a over b times my new input, which has been scaled by a factor of z to give me b z.
So AZ.
And so those cancel, and I get out an a z, like that. And so my new height here is a z. And let's take a look at the triangle we just constructed. Still a right triangle. Right? The way that I've made this thing work is I used a function, and so it must be the case that going directly above BZ, we have a straight line. So it's a right triangle. This new height here is AZ. This is B, this entire thing here is the length BZ. And we could, if we wanted to, use the Pythagorean theorem, but we already did that, right? That was the example we just did to find that this length right there, from here to there, has to be C. Z. There's no way around it. And so, is that angle the same?
Yeah.
And
Yeah.
so, is that angle the same?
Yeah.
Yeah, it has to be, right? Because if this little triangle right here was alpha, beta, 90, this one's alpha, beta, and if that's alpha, 90, then that has to be beta. And this proves what I was saying. The angles stay the same. Now, we could also talk about this in the reverse direction. So that is, in a way, this is kind of what we're going to be using all the time, is that any two triangles with the same angles, you could think about as having been scaled by a constant factor. See what I'm saying? Like, on one hand, I'm saying, if you scale it, then the angles stay the same. On the other hand, I'm saying it's also true in the reverse direction. Two triangles with angles staying the same can be thought of as scaled by a constant multiple. Does that make sense?
Yeah.
Right? So if I just drew two triangles, and we could just kind of step back and say, okay, here's two triangles. The angles are the same. Oh, well, yeah, they've just been scaled, right? And we could have worked at it in reverse like that. But that's even more abstract, you know what I mean? But you end up with the same thing. So the thing to take away from all this is that any two triangles whose angles are the same differ only by a constant multiplicative factor of every side. And this is not just true for right triangles, although that's all we've proved here. You're just going to have to take my word on it that it is true for any triangle, but we don't really care about any triangle in this class. We really only care about the right triangles. And so, yeah, we just did that. Okay, all right. Okay, coming up. So, everybody buy that?
Yeah.
Yeah.
Yeah? Okay, cool. So that was, those are the three facts. We're not going to do anything explicit like this. We do have plenty of other explicit things, but those three facts are going to be used all the time in this class, implicitly. Like we'll just have two different sized triangles and we'll say, oh, well, those angles must be the same. And it's like, well, yeah, I want to make sure that we could prove that before we just go ahead and use it on faith, right? So, okay. Where's my triangle? All right. I have not tried to do this before, so I might mess this up. So, here's 66% of your quiz. Okay.
Too probable.
What?
Too probable. It's closer to 67%.
Actually, it's closer to like 62% because in each case, there will be some things that we will not be able to get to today. But you'll see in just a second. Okay, so hold on. I am trying my best to draw an equilateral triangle. That is, every side has a... Oh, that's not bad. That's not bad at all. Oh, wow. For not having practiced this, I'm pretty proud of myself. That's... Okay, that's an equilateral triangle. And obviously not a right triangle. There are no right angles here. So what is the measure of these angles in here?
I have no idea. 180 divided by 3.
Yeah, how'd you know that? What did you assume had to be true about each of these angles?
They add up to 180.
Well, yeah.
Because all the sides are like, equal.
Since all the sides are equal, all the angles are also equal. So let's go ahead and, so that's what we implicitly did. So that's theta. You're going to see theta so much in this class. Theta. And we know that since all of, and you know, maybe you saw this proved in geometry, maybe not, but it's kind of intuitive that if all of the sides are equal length, then all the angles have to be equal too. Because again, this is all planar geometry. It's on a plane. We're not bending anything. If this were on a globe, it's possible that, well, not a globe, but if you had some kind of surface that was warped in a specific way, you could end up so that they're not, I'm sorry, just forget I said anything. They're all the same, right? And so it must be the case that theta plus theta plus theta has to give you 180. Oh, that's the same as 3 theta equals 180. And so what's theta?
60.
Yeah, because 180 divided by 3 does indeed equal 60 degrees. And so I'm going to go ahead and just relabel each one of these bad boys. 60. That guy is 60 and that guy is 60. Now, okay, we're all good there. I'll get rid of this. Now, let's give each one of these, well, it has to be the same length. And so I'm just going to go ahead and call it 2. So let's say each one of these is 2 units long. Exactly 2 units long. And what I'm going to do is take the one here on the right-hand side, and I'm going to cut it exactly in half. And because of symmetry, if that's also 2 and that's also 2, and those are the same angles there, then when I cut that exactly in half, it's also got to cut that angle exactly in half. Everybody believe that?
Yeah.
Right? Because if it weren't exactly in half, well then one would be bigger than the other, but then there'd be no way to make that perpendicular right there, or in other words, was a right angle, right? Because I'm going at a right angle away from there, exactly in the middle, leaving me what lengths here and here? 1 and 1. And so there's 1 right there. And now, we're going to forget about this guy. We don't care about him at all.
It's root 3.
And so, yeah, you remember, this length has to be what?
Root 3.
Root 3. And this angle has to be what?
30.
30. We could do that a couple different ways, because remember how we constructed it. We said, well, it was 60, and you divided it exactly in half. But what I like to do even more is just to say, well, there's a triangle. You know that's 90. You know that's 60. That guy's got to be 30, because they have to add up to 180. And so this right here, almost exactly like this. The only difference is going to be, this is what I'm going to look for. I want the degrees on the outside, because there is a better way of measuring angles. That's the way we're going to do almost always in this class. And that is what I'm going to want you to put in here and here. So this exact picture is what I call the 30, 60, 90 triangle.
Is 1, root 3, and 2. Like that.
1, 2, root 3. I do it that way because that's just how I think of it in my head. I'm like, wait, I know it's 1. Like I like to have it in order 1, 2, root 3, and so I think of it going in this direction. Of course, you could also draw it in this direction, and guess what? It's still 1, 2, square root 3, right? Like, it doesn't matter if you flip it over, the lengths stay the same, blah, 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 blah. But that right there. And then there's just going to be 2 bits. There's going to be other ways of measuring angles. And once you put those in there, that is exactly what I'm going to ask for. I will put on your quiz, draw and label the 30, 60, 90 triangle. And again, obviously, I didn't measure this out. Well, actually, I did with this one, right? So that's actually not bad. But as long as you don't do something like this, call this 60 degrees and call that 30 degrees, right? We're talking qualitatively accurate. And another thing, if you have like something like this, so that like that's 1 and then you claim that that's root 3, we say, no, that's like pretty much the same thing, right? Try to make it, you could exaggerate it a little bit, but again, qualitatively accurate, that's qualitatively accurate right there. And so let's just see, how many bits are there? The overall picture is 1, 2, 3, 4, 5, 6, 7, 8. So you could get an 8 out of 8 by doing all of this stuff. If you miss any of it, if it does not look right, that's 1 point off. If you miss the 1, that's 1 point off. If you miss the 2, if you miss the root 3, if you miss the degree measures, or we'll talk about what those are next time. But miss those. Those are the 8 points you can get when I say draw and label the 30, 60, 90 triangle. And this, being able to just pull this out of your head, this is why you're getting a quiz. Because like, not just in this class, but for the rest of your life, this is going to be, oh, were you guys good?
Yeah.
Okay.
Yeah.
So for the rest of your life, this will be one of the most useful pictures you could have in your head. Trust me on this. It's so useful to have. So now there's one more that I want to do. Not bad. What object is this?
Square.
Square. And so each of those is 90 degrees, right?
Yeah.
All of the lengths are exactly the same. And so since all the lengths are exactly the same, let's go ahead and just say it's 1, and 1, and 1, and 1. Now, let's cut this exactly in half this way. If I cut the angle exactly in half, what are my two leftover angles?
45, 45, 90.
There you go. And so I've cut that exactly in half, and so that angle is exactly the same as that angle, which is 45 degrees. By the same way we talked about last time, right? Like when I cut the 60 right in half, then I have 30 on one side, 30 on the other. This is if I cut 90 exactly in half, I have to have 45 on one side, 45 on the other. If I had 44 on one side and 46 on the other, or whatever, like this would not go exactly to that point right there. So, kind of a hand-wavy thing. It's not very rigorous, but I think it's pretty obvious that that has to be true. So we call this the 45, 45, 90 triangle. The only thing left to do, well, like I said before, I'm going to say that you put your degrees on the outside. And so we'll put our degrees on the outside. Only thing left now, besides whatever kind of magic stuff I'm going to ask for here, and you'll notice it's not an alpha and a beta, those are the same. Those are the same, right? So whatever that happens to be, we'll figure that out next time. There's one missing length. What is that length?
2.
It's what?
2. Wait. Yeah. Oh, yeah, 1 squared. Oh, 4.
No,
Wait, yeah.
it'd just be 1. Wait, no. No.
Square root of 2.
Oh. Wait.
Yep. 1 plus 1 equals 2, and so whatever c is, right? C squared, 2 equals c squared. Be very careful with that. That's like, that will trip you up more than anything else in this class. So c has to be the square root of 2. All right. Now, one thing to notice. So that's 66% of your quiz, right? Like, because there are 8 points with the other one, 8 points with this one. And again, like, this does not need to be perfect, but if you draw it like this, I'll probably give you 0 for the whole quiz. So, just try, right? And you're gonna mess. It's not gonna be perfect, but just like, don't exaggerate it. And so, yep. Okay. So, to kind of show you what I mean, like, and this is what I call the 45, 45, 90 triangle. Are there other triangles that have 45, 45, 90? Well, yeah, like we just talked about. If you take this and multiply everything by some constant amount, like, I don't know, how about 1 over the square root of 2? So if I take this and multiply everybody by 1 square over square root of 2, we end up with a new triangle, and its new lengths are 1 over the square root of 2, 1 over the square root of 2. What does that work out to be?
1.
1. Big fat 1. But it's still 45, 45, 90, just like we just talked about. And we could have made it bigger. I decided to make it smaller. How much time do we have? Let's see. Oh, it's 12:30. Perfect. So we'll stop there. But this is what I mean by the 45, 45, 90, is that in a sense, every single one of them, they only differ by a constant factor, right? If you multiply every single thing by any number, you still have 45, 45, 90. And all of these things are related, well, they're just off by one number, and we'll see why that's important next time and how we can use that to our